Okay, so let's get started. Well, before we start, does anybody have any questions on the material from this week, other than what's on the worksheet? Any questions on the homework, which is due on Monday? Okay, let's get started. So number one and number two discuss our area approximation. Number 1C discusses the exact area computation. So remember, we're going to approximate an area by splitting up that region into rectangles and using those rectangles to approximate strips of this area. So this one says we have a function, and we're looking at the intervals 0 to 2, and we're going to use 4 rectangles to approximate this area. So for this one, I'm not going to draw the function just yet. What I'm going to do, this one says find 2 approximations, right? Yeah, find 2. So you'll notice on the homework, it just says find an approximation. But this is a worksheet, so might as well find 2. We're looking at the intervals 0 to 2, and we're going to divide it into 4 pieces. So we have that division, and now we need to find those x values. Well, the one right between 0 and 2 is 1. The one between 0 and 1 is a half. The one between 1 and 2 is 1.5. And you can find them, with this one, you can find them like that. You could also find this by taking the entire interval. We're dividing the interval 0 to 2, which has length 2, minus 0, which is 2, and dividing it into 4 pieces, which tells us each subinterval will have length 1/2. So then this next one would be 0 plus a half, which is a half. Then a half plus a half, which is 1. 1 plus a half, 1.5, and then 1.5 plus 2, or 1.5 plus a half gives us 2, which is 4 halves. Any questions about dividing this interval? Okay, I'm gonna, actually, I guess I could leave that there. I might be able to fit the work over here. So now we need 2 approximations. So we're gonna have a left approximation and a right approximation. Maybe I won't be able to fit this over here. Yeah, I'll try. Let's see. So our left approximation, remember, is going to use the left endpoints on each of these intervals. And we're going to use them to help form rectangles. The rectangle's one side is going to be, in each case, 1/2. So I'm just going to factor that out here. And the rest, the heights would be given by the function at this point, the function at this point, the function at this point, and the function at that point. So I'll write this slightly smaller. So L4 is a half, the one side, times the other sides. F of 1 plus F of 3 halves. So now we have to simplify all of this. Any questions about setting up this left-hand approximation? For this, yes.
Oh, sorry.
Yes.
Just in regards to the homework, there are a couple of questions that say, set up an equation. When it says that, is this what it is asking
Yes.
for? Okay.
Yeah, it says set up 2, but yeah, this one and then the other one. You could stop right here for the ones that say just set up.
Okay, thank you.
Mm-hmm. Any other questions? Yes.
Is there any reason you aren't including 0 in the, you aren't including the 2 interval in the function?
Is there a reason I'm what? Sorry.
Because in the equation that you're currently writing, you did 0, half, 1, 2, 3 over 2, and then you didn't include 2.
Yes. So right
what
here,
is the reason that you're doing that?
Well, right here we're doing the left-hand approximation, and each of these pieces of the x-axis is going to define a rectangle. So if we look at this function, I'll just tell you right now, this function will look like this. More on that in a moment. But we're looking at the area between 0 and 2. So this triangular type area. We're dividing this into 4 pieces. We're getting these points. And then each of these, well, let's draw these lines first. So we're dividing up our region like that. But in order to approximate each of these areas, we're using rectangles. And for this first approximation, we're using, for each interval, the left endpoint. So here we're going to start with this endpoint. The function evaluated at that endpoint goes up here. And we're going to use that to form a rectangle. And for this next piece, from 1/2 to 1, we use the left endpoint on this subinterval to form the next rectangle. For this one, from 1 to 3 to 3/2, we use the left endpoint and form that rectangle. And over here at 3/2, on the interval 3/2 to 2, we use the left endpoint to form the next rectangle. So when we use the left endpoints, we're going to form our 4th rectangle without using 2. So we are just using here 0, 1/2, 1, and 3/2, and then we're adding up the areas of these rectangles. So for the left approximation, we're going to wind up not using 2. Not
Okay,
using
thank
half.
you.
Now, any other questions about setting that equation up? Okay. Let's see this form. So now we need to find these numbers, and I'm just going to write what the function evaluates to up here. Is that right? So it's 1 plus 2. Yeah, okay. So we need for this one f of 0, f of 1, f of 0, f of 1/2, f of 1, and f of 3/2. F of 0 is 4, f of 1/2 is 9/4, which you get from, well, I didn't get it from this equation. I'll mention that in a moment. But if you use this equation, you get 1/4 minus 2 plus 4. So that's 1/4 plus 2, which is 9/4. F of 1 is 1. 1 minus 4 plus 4. F of 3/2 is 1/4. If you did f of 3/2, what would you get? You'd get 9/4 minus 3/2 of 4, so minus 6, plus 4, so 9/4 minus 2, which is 1/4. Well, any questions about finding those 4 numbers? I didn't use this equation to find them. I completed the square here, because I knew this function could have been rewritten as x minus 2 squared, which also explains why I knew what it looked like. But here we substitute these 4 numbers, and what do we get? We get 1/2 times f of 0, so 4 plus 9/4 plus 1 plus 1/4. What do we get? Well, 1/2. 4 plus 1 is 5. 9/4 plus 1/4 is 10/4. That reduces to 5/2. We get 15/4, because that's what 15 halves. 10 halves plus 5 halves, 15 halves, and another 2 makes it 4 in the bottom. Any questions about this first approximation? Was there a question, or was that not a noise from my computer? Okay, that must have been a noise from somewhere else then. So we found our first approximation. This says to find both approximations. And the other one, instead of using the left endpoints to form our rectangles, we're going to form our rectangles with the right endpoints, the right-hand endpoints. And notice for this one, when we look at these subintervals, we're using the right-hand endpoints. Because of that, we're not going to use 0. We will use 1/2. We will use 1. We will use 3/2. We will use 2. The one side of the rectangle is still 1/2, but instead of starting at 0, we start at f of 1/2. then f of 1, then f of 3/2, then f of 2. Is that showing up on the screen? Yeah, okay, so for this one, instead of starting at 0, we start at 1/2, and we end at 2, because we're using our right endpoints. And we also notice we need f of 2, which is 0, because you get what, 4 minus 8 plus 4. So substituting all of this in gives us what, 1/2. F of 1/2 is 9/4. F of 1 is 1. F of 3/2 is 1/4. F of 2 is 0. So what do we get? We get 5/2 plus 1, 7/2. 7/2 divided by 2, 7/4. So we have 5/2 from those two, plus 1 makes 7/2. 7/2 with another 2 makes 7/4. So any questions about these? Well, about part A. Before moving on to part B, I don't think I asked this, did I? Yeah, before moving on to part B, let's observe. Is this an over approximation or an under approximation? So, well, I have the drawing. It's kind of a mess. So I'll just write observe. L4 is an blank, and R, well, is an blank hyphen approximation. And R4 is an well, I should abbreviate both, but I abbreviated one. So the question here, or the observation, is which one of these is an over approximation and which one is an under approximation? And to do this, I like to consider what the graph looks like. And this graph, well, I already drew it before, but it's not currently on the board. So let's draw this graph, x minus 2 squared. We can do that by completing the square. This is already a perfect square. But x minus 2 squared, marker's running out. I don't have another black marker that works. That's a lot to try. Does the blue show up? Yeah, okay, that blue is showing up. This is a little faint. So right here, the function is x minus 2 squared. So it goes, so it's x squared shifted to the right 2 units. And we have this region. So if we form our rectangles using right endpoints, or sorry, using left endpoints, we'll have that drawing I had before, but each rectangle is more than the actual area that corresponds to that strip. So the left-hand approximation is more than the actual area. So L4 would be an over approximation, and similarly, the other one would be an under approximation because the rectangles are smaller. Or once you find one of them, then you know the other, unless they're equal, which I don't be for any examples. Any questions about that observation? Okay. Part B, set up two formulas which approximate the area between this function and the x-axis interval 2 to 5 using 7 rectangles. So here we need the set up formulas, so we don't need to simplify. Just need to make our answer look like 7 rectangles. So what do we have? 2 to 5 using 7 rectangles. So we don't even need to know what the function is. So I'm not even going to write out the function, but we do need to know the interval 2 to 5, and we're dividing it into 7 pieces. 1, 2, 3, 4, 5, 6, 7. But to do this, we need to find these x values. And how are we going to find them? Well, we have this interval 2 to 5, which has length 3. 5 minus 2. We're dividing it into 7 pieces. So each of these subintervals will have length 3/7. If each subinterval has length 3/7, well, we can then find this first one. Because this first one would be 2, and then over another 3/7. 2 plus 3/7 is 2 3/7, which is also 17/7. Any questions about finding that first one? I'm just going to rewrite that as 14/7 since last one is 35/7. So any questions about finding this 17/7? So now from here, the next x value is 17/7 plus another 3/7. So 20/7. And we keep going with that pattern, 20/7 plus 3/7, 23/7, 23/7 plus 3/7, 26/7, 26 plus 3, 29, 29 plus 3 is 32. It's not a 7. And then the last one, 32 plus 3, would give us 35/7, which is 5. So we did not make a mistake in our addition. Any questions about finding these? Observe, if you force all the denominators to be that number, then the numerators will follow that sequence, 14 plus 3 plus 3 plus 3 plus 3, and so on. But now we need our approximations. So L7 and R7. Well, with our approximations, we're still using rectangles, and the one side of the rectangle is still 3/7 in each case. But the other side for the left-hand approximation is determined by the left endpoints. Of those 7 subintervals. So we'll start here at 14/7, and for this I'm just going to change that back to a 2, because we don't want unreduced fractions all over the place. They were just to observe the sequence. So 2, the first rectangle is formed on 2, so f of 2, and then we keep going. F of 17/7 plus f of 20/7 plus f of 23/7 plus f of 26/7 plus f of 29/7 plus f of 32/7. That's a 7. Both times I had to write a 2 as the ones digit. I wrote a 7 in the denominator. Two and 7 look kind of similar. That last one says f of 32/7. In case that's not clear, looking at my computer, it looks like it may not be that clear. But we stop at our last left endpoint. Any questions about the left-hand approximation setup? Now for the right one, instead of using the left endpoints, we use the right endpoints. So we start, in this case, at 17/7, we end at 5. So f of 17/7 plus f of 20/7 plus f of 23/7 plus f of 26/7, f of 29/7 plus f of 32/7 plus f of 5. So definitely do observe that these 6 in the middle are included in both. The only real difference in our approximation is which endpoint we include. Any questions about this one? So for setting these up, that's all you have to do. I mean, I wouldn't have you evaluate that function, all these numbers. That's not a good use of your time. But setting it up is. So any questions about that? Next, set up and evaluate a limit which we can use to find the exact area between the function and the intervals 0 to 3. Recall those relations, and we will recall them when we get there. How do I want to start? Let's start area. So we're dividing, in this case, the interval 0 to 3, which is not drawn to scale, but we're dividing an area into a bunch of strips. And what we're doing, we're observing, is that as we use more and more rectangles, this piece, which is preventing our approximation from being exact, gets smaller as we use more rectangles. And in the limit, where the limit is taken to infinity, in that limit, when we let the number of rectangles get large, that error term goes away. These pieces in the limit go to 0. So as we let the number of rectangles go to infinity, the approximation becomes exact. So I'm not going to write this, but in this, maybe I should write it for this one. Let n equal the number of rectangles. Let n be the number of rectangles. So what we're going to do is set up an approximation of the area with n rectangles, and then we're going to let that number go to infinity. I'm going to do that in one step. So the exact area will be the limit as the number of rectangles go to infinity of the approximation. The approximation is given by a sum of n rectangles. So the limit will make this approximation exact, and here we're going to add n rectangles together. So what would a general rectangle look like? Well, there are a couple ways you could start the next thing that I'm going to do. I'll do it like this. I'm not going to draw the function. I'm just going to draw an x-axis interval. 0 to 3. So in previous examples, we divided our interval into a number of pieces. When we did the first one to 4 pieces, we did the next one into 7 pieces, but here we're using n rectangles. So we're dividing our interval into n pieces. So we take our interval of length 3 minus 0. We're dividing that into n pieces. So that tells us we're dividing the interval into n pieces. That tells us the length of each piece is going to be 3 over n. Any questions about where this is from and what it means? So all we've done so far down here is observe that we're dividing the interval 0 to 3 into n pieces. Next, we're going to label these x-axis values. Maybe I'll draw this a little bigger, because this might take up some more space than that. So we have 0 to 3. Each of these subintervals has length 3 over n. So what is this first one? This first one, well, we start at 0, we go over 3 over n. 0 plus 3 over n is 3 over n. Any questions about that first x value? I would say finding that first x value is one of the more important, probably the most important thing when setting this up, being precisely sure where this 3 over n comes from. So divide the interval 0 to 3 into n pieces, and this first x value would be 0 plus 3 over n. So any questions about that? Okay. The next x value, well, we start at 3 over n, we go over another 3 over n. So we have 3 over n and another 3 over n. Well, 3 over n plus 3 over n is 6 over n. But if we write it as 6 over n, it's not going to be as illustrative as if we write that in another way. Because right here, we're going to be counting through our n rectangles. And we're going to be counting through them using this 3 over n. So it would be particularly useful if we could write these x values in terms of 3 over n. Well, the first one's just 3 over n. The next one is 3 over n and another 3 over n. Well, 3 over n and another 3 over n is 2 3 over n's. So instead of writing it as 6 over n, maybe I'll write it like this: 6 over n, which equals 3 over n, not 3 over 6 over n, which equals 3 over n times 2. So this first one, 0 plus 3 over n. The next one, 3 over n and another 3 over n, which for using this equation, we will interpret as 3 over n times 2. Any questions about that? So let's find the next x value, or the next x value. Well, here, 0 plus 3 over n, plus 3 over n, plus another 3 over n. So we went over 2 3 over n's to get here. The next one would be this 2 3 over n's and another 3 over n, which is 3 over n times 3. It's 3 copies of 3 over n, which is also 9 over n, but that 9 might just get in the way. And you can see a pattern developing. Because here, I didn't write it, but here, there's 1 3 over n. So this is 3 over n. This is 2 3 over n's. This is 3 3 over n's. The next one would then be 4 3 over n's. And so on, until you got to the last one, which would be n 3 over n's. The last one, n 3 over n's, which simplifies to just 3. So any questions about this labeling of our x-axis values? So now that we have this, we're going to keep rectangles in mind. Because the sum, we're adding together areas of rectangles. So we should have in there 2 pieces, a length and a width for our rectangle. Well, the one side is still going to be given by the length of this piece or that piece or whatever piece, which we already found to be 3 over n. So we have the one side of our rectangle is 3 over n. Now, the other side of our rectangle, there are 2 approximations you could use. Those sum formulas which are given will work most conveniently if you use a right-hand approximation, but the notation we're using is going to set up a right approximation by default. Meaning, if you stay consistent with I equals 1 to n and a labeling like this, it will always turn into a right approximation, a right-hand approximation. But what we're going to observe is that this I value in going from 1 through n is going to count through our rectangles. And it's going to count through our rectangles using this number, which is, you'll notice, just going 1, 2, 3, 4, and so on until the last one, which is n. But we can't just say it's this number and this number, because we need to form our rectangles. And to form the rectangles, we need to take our function and evaluate them, or evaluate it at each x value. So we need our function evaluated at this number where I is going to stand for what is counting through. So we have 3 over n times I. I'll just put that I in the numerator for now. So we get 3i over n. we're evaluating our function at 3i over n, and I counts through our rectangles. Any questions about setting that up? Okay. This type of problem, I do think takes some time to get used to. We're not done yet. We have to actually find the area. I just need to erase this so I have room. So we will revisit this this type of problem later in the semester. But you know, it is good to try working on now, see what makes sense now, and then later on, you can build on what makes sense. Because when you let math stay in your mind for a few weeks, your mind can really do interesting things with it and force certain things to make sense. And it could also make very clear which parts don't make sense. And a problem like this could certainly show up on the final exam. It will not show up on exam 1, but we are still going to go over it now, so that when we go over it later, it becomes more clear as the semester progresses. So now we need to evaluate this. Well, first we're going to evaluate our function at 3i over n. So leave everything else alone. We need to evaluate the function at 3i over n. Well, 3i over n for all x's. Three I over n for all x's gives us that quantity, and let's just simplify that square in that distribution. So 3i over n all squared is 9i squared over n squared. Negative 4 times 3i over n is negative 12i over n, and 4 is 4. So evaluating our function at this x value gives us that. Any questions about getting there? Okay. Now what? Well, I don't have to erase that yet. I can write one more line. We still haven't taken a limit. We still haven't dealt with the sum. We're just evaluating what's inside the sum. Now, the next thing I like to do, I always like to do these the same way every time. I don't like to jump over a step because there's a lot to deal with in this. You could, at this point, jump straight to using those given formulas. But before doing that, I always like to just distribute this 3 over n. Distribute the 3 over n. What do we get? Yeah, I guess I'm going to erase that. Well, in this first one, 3 and 9 make 27. I squared is still there. N and n squared makes 3 n's, which is n cubed. The next one, 3 and 12 and a negative make a negative 36. I is I. N and n make an n squared. And for the last one, 3 over n times 4 is just 12 over n. And we still haven't dealt with the sum. Any questions about getting here? Okay, now we're going to deal with the sums. The formulas given tell us how to deal with the sum of I squared, the sum of I, and the sum of 1. Which I don't write, but there's a 1 there, 12 over n times 1. And the sums will, well, using the sums allows us to, well, get rid of the sum and all of the i's if we're careful in our organization. And what I mean by that is for this first one, before even thinking about the sum, I like to write down the things that aren't the sum and I, meaning in this case, I like to take that 27 over n cubed out. and then deal with the sum of I squared, which is n plus 1, 2n plus 6, all over 2. Oh, wait, what am I doing? I can't memorize formulas anymore. When I was younger, I was able to memorize formulas. So n plus 1, 2n plus 1 over 6. So this first one, the sum of I squared, turned into this, and then 27 over n cubed just carries along. The next one, we'll do the same thing. We still haven't taken a limit. 36 and n squared we'll take out first. And then we're left with the sum of I, which this page tells us is n plus 1 over 2. And then we'll do the same thing for this last one. Take out the 12 and the n, and we're left with, if we factor out a 12 over n from this, we're left with a 1. And the sum of 1 is just n, because it would be, what, 1 plus 1 plus 1, n times. Any questions about getting rid of the sum? The sums. Okay, now from here, we can use the coefficient observation we made in workshop last week, because notice, well, let's notice the middle term now. So right now, I'm just going to look at that piece. What happens if you multiply that denominator? Well, you get 2n squared. What happens if you multiply the numerator? Well, you have n squared plus n times 36. So if you I think is that showing up? That's not that clear. So in this middle term, if you distribute everything out, in this, if you multiply everything out, you get negative 36. Oh, that's negative. What am I doing? Negative 36n squared minus 36n over 2n squared. So in particular, we have a degree 2 over a degree 2. And in that case, we could divide everything by n squared and then take the limit. Or we could make our coefficient observation, which would tell us that this limit would be negative 36 over 2, which I will write over here as negative 18. Any questions about that middle one? Well, there should be a question because that camera is not low enough. Maybe that's not a question, more of a remark. Okay, that's showing now. Any questions about getting that negative 18 from here? Now, notice, if you didn't want to multiply everything out, which I don't want to multiply everything out over here, and that's a lot of things to multiply. But notice, we have in the bottom an n squared, and we have in the top two things with n's multiplied. So that'll also make an n squared. So we could jump straight to a coefficient argument by observing the numbers on the ends. So here on the ends, we have a 36, 1, 1, which make and a negative 36. In the bottom on the ends, we have just a 2. Or, sorry, on the n squared, we have a 2. But either way you want to conclude that this middle one simplifies to negative 18 is fine with me. So any questions about the middle one? Okay, the last one here we'll just take care of now. The n's cancel and you're just left with 12. And as n goes to infinity, 12 doesn't change, so that's just 12. But we still have this first one to deal with. Well, what do we have? We have in this one, in the bottom, an n cubed. In the top, we have 3 things with n all multiplied together, which will produce another n cubed. So what coefficient would be on n cubed? Well, there's a 27. I'm going to write, I guess, the side work over here. I'll just write these coefficients over here. On the n cubed in the top, we have a 27, a 1, a 1, and a 2. So that's a 27 times a 2. In the bottom on the n cubed, we have just a 6. So we have 27 times 2/6, 27 divided by 3, which is 9. So the first one, we have a 9, second one, negative 18, third one, 12, which makes the exact limit 3. Any questions about this one? Not an easy computation, but always keeping in mind n is rectangles, and we're trying to add areas of rectangles. That's I think that's the most important first observation, that a formula like that is forming our rectangles. So any questions about this one? Okay, and we will revisit this later. This exact type of computation, just like this, would not be on exam 1, will not be on exam 1, maybe on the final when we get into chapter 5. Before moving on to number 2, yeah, we should have enough time. Yeah, that should definitely be enough time. I'm going to ask one more question about this one. This one said, so if you compare this one to the one we covered in the notes, the formula looks slightly different. In particular, that last part of the formula looks slightly different. What if instead of the interval 0 to 3, we used the interval, let's still make it length 3. Let's say I used 1 in the lecture. Maybe I shouldn't use 1 this time. Yeah, let's use 1. What if we asked the same exact question and wanted the interval 1 to 4? And the question would be, what in this formula is different? There's actually not much that will be different, but so this isn't saying what if we used it, what would the final answer be? What if we used 1 to 4? What in this formula would change? And I'd like you to think about that for about a minute, maybe draw out a number line and take your 3 over n's in that. So I'd like you to see what happens there for about a minute while I go get another marker from our supply cabinet. So I'll be back in a moment, but definitely try that. It's very useful to keep in mind how that would change. Okay, I will give you the answer now. It would differ by changing that to a 1 plus 3i over n. And why would it do that? Well, if you took the interval 1 to 4, we're again dividing it into n pieces. So we again get 3 over n. But if you look at the x values, instead of being 3 over n, this would be 1 and another 3 over n. And the next one would be 1 plus 3 over n plus 3 over n. And so on. So any questions about that? The rest of it would still be the same. N rectangles, let that number go to infinity. The length of the one side is still 3 over n, but the function is, in a sense, being shifted over 1. Well, maybe not the function. Our rectangles are being shifted over 1. So any questions about that one? So that also wasn't on the worksheet. I don't know what that exact area would be. It would be something. Okay, let's do number 2. 2. Let f of x be sine of x. Okay. Find 2 approximations for the area between f of x and 0 to pi over 2 using 3 rectangles. So we have the interval 0 to pi over 2. We're using 3 rectangles. So let's label 0. Let's label pi over 2. We're dividing this interval, which has length pi over 2, into 3 pieces. So each piece will have length pi over 6. If each piece has length pi over 6, well, the first one, 0 plus pi over 6, pi over 6 plus pi over 6, which is 2 pi over 6, which is pi over 3. And then the last one, 3 pi over 6, which is pi over 2. Any questions about the x-axis interval? And breaking the x-axis interval into 3 pieces here. Okay. I'm going to erase that now. So we need 2 approximations, L3 and R3. So L3, rectangles. The one side is pi over 6. And the same for R3. But for the left-hand approximation, we're going to use our right. Sorry. For the left-hand approximation, we're going to be using our left endpoints. It's very common that I mix up left and right. So for our left-hand approximation, we use the right endpoints. For the right-hand approximation, we use the right endpoints. And I always, when doing these, just wind up filling in the dots for the left one and then putting a large circle for the right one. But the right endpoints start at pi over 6, then go to pi over 3, then go to pi over 2. And this one doesn't just want us to set them up. We actually have to solve these, so let's do that. So we need f of 0. Sine of 0, what's sine of 0? Well, sine of 0 is the y value there, so 0. Sine of pi over 6, what's sine of pi over 6? Well, we have our triangle. Sine of pi over 6, opposite over hypotenuse for that is 1/2. Next, we need sine of pi over 3. Sine of pi over 3, opposite over hypotenuse for that, √3 over 2. And then the last one we'll need for the next approximation, sine of pi over 2 would be the y value up here, 0, 1, so sine of pi over 2 is 1. So for this, what do we get? Pi over 6 times what? 0 plus 1/2 plus √3 over 2. What is that? How simplified do I want this? You could leave your answer. I don't have much room. You can leave it like that if you want. You could also make it √3 pi plus pi over 12, or you could say pi times √3 plus 1 all over 12. Or you can leave it like that. However you want. You can. I personally think that one looks the nicest, but whatever. Any questions about the left approximation? If you turn that into a decimal, it's incorrect because it needs to be exact. How about this other one? Well, pi over 6. F of pi over 6 is 1/2. F of the next one is √3 over 2. F of the last one is 1. So what does this equal? Well, here 1 is 2/2. That's a 6. So 1 is 2 halves, 2 halves and 1 half make 3 halves. Root 3 plus 3 is root 3 plus 3. So pi over 6, and then 1 half plus 2 halves gives us 3 halves. Root 3 over 2 is root 3 over 2. Any questions about this one? Okay, so on exam 1, so it's based on the first 5 weeks. In week 1, we did do just evaluate sine and cosine and the others at something. So on exam 1, there won't be questions like evaluate sine at something, but you could have a question like this, where it's a calculus question, and inside the calculus, you do have to know these evaluations. So any questions about this one? Okay. The last 2 are on the derivative, and the derivative, we will be using the derivative for several weeks. It's arguably the most important thing covered in any calculus class, especially a Calc 1 class. It's the most important thing because it takes up more than half the semester. But to start the derivative, we will start by defining the derivative. And the definition of the derivative is very important. Next week, we will learn other ways to compute the derivative without the definition. But the definition is very important because it ties the next 8 weeks into the limits, which we already covered. So let's start with using the definition of the derivative on this function. 5x squared plus 2x minus 3. So first we need f prime of x. F prime of x is a new function, which we call the derivative, and it's defined by this limit. Limit h to 0, f of x plus h minus f of x over h. So here we're using our original function in this equation to find a new function. Well, so what is this? Well, f of x plus h, replace all x's with x plus h. So right here, there is f of x plus h. Any questions about finding f of x plus h? So in this substitution, we're using the given function. We're not using 10x plus 2. My reason for, in part A, writing 10x plus 2 was so that you knew what this should eventually simplify to. So f of x plus h, replace all x's with x plus h, minus f of x minus all of f of x. If you don't subtract all of f of x, it won't simplify nicely. Well, it won't simplify enough. And it's all over h. Well, let h equal 0, you get 0 over 0. So we have to do algebra. It's set up to give you 0 over 0. What algebra can we do? Well, we can expand everything in the top. And what do we get? X plus h all squared is x squared plus 2xh plus h squared. So there should be a 2 there. I'm not writing it because I don't want to erase it. X squared plus 2xh plus h squared all times 5 gives us 5x squared plus 10xh plus 5h squared. So x squared, 2xh, h squared with an extra 5 on everything makes 5x squared, 10xh, 5h squared. Distribute this 2, we get 2x, we get 2h, negative 3 is negative 3. Distribute the negative, negative 5x squared, negative 2x, and a positive 3. Any questions about what we've done so far to simplify this? just distributed everything, squared that. And now a few things should cancel. What will cancel? Let's see if this other marker works. What cancels? Well, we have a 5x squared and a negative 5x squared. They cancel. We have a 2x and a negative 2x. They cancel. We have a 3. I don't have another shape. Triangle. We have a 3 and a negative 3. They cancel. So everything which is currently shaped adds to 0. If you didn't distribute as negative, you wouldn't get enough canceling. But all of those in the numerator add to 0. And what are we left with? We're left with still a fraction with h in the bottom, but there's less in the top. We have a 10xh, we have a 5h squared, and we have a 2h. Any questions about that step of simplification? So all of those added to 0, except for this. And now, if you let h equal 0, you again get a 0 over 0, but notice all of these terms have an h, so you can cancel an h from each thing. And what are you left with? Cancel an h from that, you have 10x. Cancel an h from that, you have 5h. Cancel an h from that, you have a 2. Cancel an h from the bottom, you divide by 1, which we won't write. And now we can let h equal 0. Letting h equal 0 gives you 5x plus 0 plus 2. 5x gives you 10x plus 0 plus 2. So you get 10x plus 2, which is what part A told you you should get. If on a test the directions say to use the definition of the derivative, you have to use the definition of the derivative. It's very important in calculus to see that what we're doing for the next several weeks ties into what we did for the first several weeks. So if it says use the definition, you have to use the definition. Those of you who have not seen calculus, by next week, we'll have more of an idea why I'm saying that seemingly obvious statement so many times. If you're told to use the definition, you have to use the definition. Any questions about 3-part A? So next week, we will learn a way to get here to here in essentially one step, for those of you who've not seen calculus. But that is next week. And on the test and on the final, there will be a question that says, use the definition. It'll definitely be on exam 1. It'll definitely not be on exam 2. And it'll definitely be on the final. Use the definition for one of them. So any questions about 3-part A? Okay, now 3B and 3C are ways we can use the definition of the derivative, because this is set up to give us the slope of a tangent line at a given x value. After exam 1, we'll learn another interpretation using velocity. But for now, our interpretation will be that we can use it to find an equation, or to find the slope of a tangent line. And part B says find an equation for the line tangent to f of x when, I should put point first. Find an equation for the line tangent to f of x when x equals, I think I wrote -1. Yes, when x equals -1. So for part B, we need a point, we need a slope, we need a point, we need a slope. Well, the point is given by the function at -1, the original function at -1. So you get what, 5 minus 2 minus 3. So you get negative 1, 0. So 5 minus 2 minus 3 gives us our y value for the point. So the slope, we can find the slope for a tangent line by using the derivative. So f prime, in this case, at negative 1. Well, f prime is given by that formula. Let x equal negative 1 down there, and you get negative 10 plus 2, so negative 8. And an equation for the line would then be y minus 0 equals negative 8, x minus 1. And then, if you want, you can just write that as negative 8. Let's get rid of the 0 if you want. If you don't want to get rid of the 0, you don't have to, but I get rid of the 0 if it's a 0. That's not right. What am I doing? It's always good when you're done with a question to take a step back and look it over. So I just took a step back and noticed that I jumped over that negative sign. So it should be negative 8x plus 1. Negative 8x plus 1. Any questions about part B? Okay, part C, find all x values at which f of x has a horizontal tangent. Well, what does a horizontal tangent look like? Well, a horizontal tangent looks like that, where you have a tangent line that's horizontal, or it could look like that. But in particular, a horizontal line has slope 0. So we're looking for the x values at which the tangent line has slope 0. So for part C, we need the x values which make f prime of x equal 0. So here, f prime of x is 10x plus 2. Set that equal to 0. You get x equals negative 1/5. Is that showing on the screen? Yeah, so x equals negative 1/5. Subtract 2, divide by 10, reduce the fraction, and you get x equals negative 1/5. Any questions about this one? What was that, number 3? Okay. Number 4. Use the definition again on x to the 5th plus 2. Use the definition of the derivative on this. Well, again, the derivative f prime is given by the limit as h approaches 0 of f of x plus h. So there's f of x plus h. Replace all x's with x plus h. Minus f of x. Subtract all of x of f of x, so that, notice here, those 2's will eventually go away, all over h. So now again, we have some algebra to do. We need to expand that x plus h to the 5th. And to do that, I like to use Pascal's triangle, because actually writing out x plus h times x plus h times x plus h can get exhausting. So we're going to have a long thing here for x plus h to the 5th, and then we'll write the rest. How do we use Pascal's triangle on this? Well, I'll do it as side work. Start with 1, 1, 1 like that, and then keep filling in the rows by adding up the 2 numbers immediately above it. Start with a 1, end with a 1. In the middle, 1 plus 1 is 2. Here, 1 plus 2 is 3. 2 plus 1 is 3. And with a 1, we need 5 to show up in the second position. So we need to keep going. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And with a 1, Well, that's not a 5, that's a 4. So we need to keep going. 1 plus 4 is 5. Well, that's a 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then it ends with a 1. So right there, we're going to expand using that row. And I'm going to do more side work over here and then just transfer the answer up there. So we have those coefficients. I'm going to write them out. With space. And now we have an X and an H. And we need 5 total letters on each piece. We're going to start with 5 X's here and go down 4 X's, 3 X's, 2 X's, 1 X, 0 X. And the opposite with H's. So we'll start with 5 X's, and then put 4 X's, then put 3 X's, then put 2 X's, then put 1 X, then put 0 X's, which you don't even have to write if you don't want to. And we do the same thing with H's, but in the opposite order, meaning put 0 H's here, 1 H here, 2 H's here, 3 H's here, 4 H's here, 5 H's there, and all of these get added together. Well, now we'll just write our answer up there without all these 1's written. 1 times x to the 5th times 1 is just x to the 5th. That h to the 1 is just h, so we have plus 5, x to the 4 h. Nothing can be rewritten there, so 10x cubed h squared. And over here, 10x squared h cubed. Over here, 5x h to the 4. And there we have h to the 5th. Yeah, I definitely should have started writing that more over. It's okay. So we expanded this binomial to the 5th power. Any questions about that expansion? Now, on a test, odds are basically 0 that I would ask you anything 4 or larger. But on a worksheet, I could. Plus 2 minus x to the 5th minus 2. So any questions, all over h, about the algebra we did up there? Now I have to erase it. So let's look at what happens here now. Well, you let h equal 0, you'll still get a 0 over 0. But notice x to the 5th and negative x to the 5th cancel, as do 2 and negative 2. So let's write this without those. We're still left with a 5x to the 4h, a 10x cubed h squared, a 10x squared h cubed, a 5xh to the 4, and an h to the 5th. And all of this is still divided by h. All we did was add those 4 things in the top to 0. But now everything has an h. And if everything has an h, you can take an h off of everything. And you're left with here just 5x to the 4. That's a 4, that's a lousy 4. Here you're left with 10x cubed h. Here you're left with 10x squared h squared. Here you're left with 5x h cubed. Here you're left with h to the 4. We still haven't taken a limit, so we still have limits all over the place. But now we can take the limit by letting h equal 0. This term won't change as h goes to 0. That goes to 0, that goes to 0, that goes to 0, that goes to 0. So you just have 5x to the 4th. Any questions about this one? So again, on a test, the largest exponent I would ask on a test would be a 3. But it is nice to see this, especially for a proof we do next week. So, you know, it is definitely worth observing how in this computation, the only thing that wound up mattering was that second piece. So all of these other things that we expanded using Pascal's triangle went away in the limit. And that'll be a useful observation for a proof we do next week, where we talk about some algebraic ways we can compute the derivative. So are there any questions on this worksheet? Okay, any questions on the homework for next week? There's a typo in problem 1. It says find asymptotes for f of x, and there's no f of x, or it says limit instead. Should say f of x equals that function. And it's not an overly bad typo, but I just noticed it today when I wrote solutions to it. But if there are no questions, well, I guess we're ending about a minute early. So I hope you have a good weekend. I hope the homework goes well. It should be straightforward. I did just do it. And the numbers work out in a sort of convenient way. So I hope you enjoy your Thursday, and I hope you enjoy your weekend. And well, the test is a little less than 2 weeks away, so that's definitely worth thinking about this weekend. But I hope you enjoy your time, and thank you for showing up.
Thank you.
Thank you very much.
Thank you.